Thank you. Thanks for the introduction. My name is Rizo, and I wanted to share today with you my experience of building a front-end development framework in OCaml. And specifically, I wanted to share my experience building a modern front-end development framework in OCaml. And many of you might be like, modern, you know, what does it even mean? Like, what's modern? Is modern even good? I feel like in engineering, modern sometimes means like, I don't even know what it means, like marketing, right? Well, last year, my wife and I decided to build a house. And many people were like, are you going to build a modern house, you know? And I was like, sure, like I kind of like how they look, you know? They have like flat roofs, you know, like nice lines. Yeah, I knew nothing about modern architecture. So I decided to fix that and sort of learn what modern architecture means. And I'm going to use the definition of modern architecture as a guiding principle to design this modern web framework for OCaml. So it turns out that modern means functional. Isn't that cool? Form follows function is one of the central, themes in modern architecture. And what it essentially means is that the way something looks should be the way something works. Intention and purpose should be the guiding principles, not the aesthetics aspects of architecture, but the functional bits. And that also means that houses sort of become like machines for living, a housing machine for living. That's quite deep, right? Well, but we also don't want to live in like machines, right? We don't want to live in factories. So modern architecture is not just about function, it's also about harmony. It's about organic architecture. It's about integrating with the environment, integrating with the nature, and sort of embracing the natural constraints that exist in the world, as opposed to trying to fight them. Modern architecture doesn't stand out. Oh, this is much better. Modern architecture doesn't stand out. It's minimal. It does just what it needs to do. Less is more. And, in particular, we want to get rid of all of the unnecessary decoration, ornament. We just want to keep the bare bones, minimal, things that are required for our building to work. And if we do that, what's left is just raw materials. Bricks, raw cement, in this particular case, glass, metal. So modern architecture is quite innovative with the way materials are used to achieve structural integrity. And if we succeed in doing all of this, we get timeless architecture as well. So what timeless means is that, if you have good design today, it's going to be good design in 50 years, in 100 years. So to sum it up, these are some of the principles that we are looking at when we speak about modern architecture. And now is the fun bit. What does all of this mean for front-end development in OCaml using signals? So this is my interpretation of that. Okay, form follows function. I think this is all about component composition. We want to make sure that our forms are functional, composable, and they directly reflect the purpose of our program. Less is more. We want to keep our API surface really small, just the essentials. No extra stuff. No ornaments. Forget about all that complicated syntax, PPXs, MLXs, GSXs, I don't know, Let's just use the language. Timelessness. Is this still working? Timelessness. I think OCaml and GS of OCaml have been around for quite some time. They've stood the test of time, and we want to build on top of that. And, Antonio has convinced us today that Melange is sort of on a path to get there, so maybe I'll reconsider at some point, and I'll implement support for Melange soon. But for now, let's just focus on these tools that we have at our disposal. Material honesty. So instead of hiding things, we want to make them explicit. Instead of pretending that we have, reactivity happening magically, we want to make it explicit. We want to have a type for that. And I'll talk more about what I mean by explicit reactivity in a bit. And finally, for structural innovation, instead of using VDOM, we're going to be using signals. And there's one last final piece, which is flat roofs. Can anyone guess what flat roofs could mean for us in this context? Like, really? Right? Is this whole thing going to be about monads? Well, we'll see about that. Okay, so to talk a bit more about the explicit reactivity bit, I wanted to show you one example. And this is React, you know. This is like the contemporary architecture, so to say. Modern architecture, isn't it? Well, let's see how modern is it. I guess like by just looking at your faces, I can tell exactly who knows React and who doesn't. Is there something wrong with this code? Well, of course, we can't just do that, right? Because you know, this component is going to render, and then it's going to re-render, and then we're setting intervals again and again. It sort of like creates all sorts of different problems. So we need to fix that. Let's do it. Is this better? No. Okay. Why isn't it better? Well, because now we're only doing it once. So we have captured this count variable in the beginning for the first time. We said, hey, just do it once because we don't have any dependencies in use effect, but the count is not going to update. So there's a solution. We add count. Is this fixed now? No. Because if this use effect is depending on count, it means that we're back to the same problem of recreating the set interval again whenever count changes. So what's wrong here? What's happening? Well, this is a pathological kind of problem. It's better described in Dan Abramov's article about making set interval declarative. And look at this code. I mean, I think React is an amazing framework. Don't get me wrong. I think it's like revolutionary because it brought so many people to like declarative composable UIs, and we can't just ignore that. But at the same time, I feel like this stuff is just fighting with the natural environment, you know? It's not organic architecture, sorry. I can explain you what's happening here. It's like when this renders, we need to save the callback that's going to be storing the state every time the component updates, so that whenever we call the tick for the interval every second, it's using the latest value, but like, let's not do that. And you know, he talks about like impedance mismatch between React and the programming model in the stateful APIs in the browser. And I think that's fair, but you know, let's look at some of the other problems that we have in this code. So counter is a rendering loop. It's not just a function. And to me, this is, you know, it doesn't work like it looks. It's not form follows function. There's going to be unnecessary re-renders if we're not careful with all of the state management, use callbacks, and so on. So, you know, dependencies have to be managed explicitly and manually, and if we forget one of them, all sorts of things can happen. And I know it's fine in React because it's supposed to like re-render and like settle down and so on. But what if we use different materials to build this? What if we use signals? This is what I'm proposing to build. So in this case, we want to set up a function that is called just once. We want to create a signal that has the current count and the ability to update that count. And we set up interval to call emit, so to increment the count every time the timer is triggered. And then in the end, this is reactivity. This is the explicit reactivity that I was telling you about. So the only thing that's going to update whenever our signal is changing value is this piece of HTML there. And you know, reactivity is explicit here. We are being opt-in about all of this stuff that's dynamic in nature. And you know, some of you might be like, oh, but what about cleanup? I don't think there's an impedance mismatch between declarative, functional, and the browser APIs. In fact, I think the browser APIs are quite nice, and you know, they provide you with very low-level tools to achieve some of the functionality that we want. So in this case, I'm proposing to use an explicit resource management function whose job is to essentially acquire a resource and free it whenever it's no longer needed. And you can see in this example that we're essentially still rendering the same HTML. We're just scoping the lifetime of that resource to the HTML going to be rendered for the component. All right, but like, what is a signal? You know, like, how does all of this work in reality? Signals are essentially values. You can really think about them just like integers, floats, strings, lists. The only difference is that they change over time. And not only they change over time, you can subscribe to those changes. You can say, hey, I'm like interested in that integer. I want to get an update whenever it changes. And that also means that someone needs to change it, potentially in a different part of your application. We also want to combine signals, derive signals, manipulate signals, just as we do in normal functional programming, with map, filter, reduce, and all of those things that we already know. We don't want to hide that. We want those materials to be visible to us. We want to know if something is reactive. And finally, we want to do some optimizations and so on to like batch updates and prevent unnecessary updates and so on. But that's just like implementation details, really. So first time I heard about signals, I was like, I can do this, It's like, if I need to subscribe to something, this is the type. And I really like this type. I think it's probably one of my favorite types. It's kind of like paradoxical because it's like, if you give me something, I'll give you something, and then what? Like, seems like nothing's going to happen. Unit, right? Like, what's happening there? But let's see if we can actually make this useful. So let's define a signal, a value that satisfies that type, like emit once. We get a k, and we just push a value down that k. That's it. So if we then instantiate it and use it, this is what happens. We just get the values. Is this a signal? No. This is just like fancy and like convoluted function application, really. The only thing we're doing is calling emit once, like, passing the value to printf, nothing else. So what's missing? What do we need to add to this to make this a signal? We need to give it the ability to publish values externally. So we want to allow it to not only give us the way to subscribe, but also give us a way to publish something so that it becomes useful. And the implementation is pretty trivial. We still have the same sub, but instead of publishing the value immediately, it just parks it. Just keeps it in a mutable list and does nothing else. And whenever someone calls emit, we iterate on those consumers and we dispatch the values. So it's interesting because signals are a form of concurrency. And this is concurrency, by the way. Like, it might not seem like much, but this is concurrency. It's not very fancy. We could make it a bit more sophisticated, but the core idea behind concurrency is just this: parking interested parties and then later waking them up and giving them something. So if we use this, what's going to happen? Well, nothing's going to happen because we just subscribed. We haven't pushed the values. We haven't emitted the values. But of course, if we actually call, emit, and so on, then the values are going to be propagated down to the subscribers. Now, the interesting thing is that you'll notice that the order here is sort of flipped. And that's quite intentional and natural in this case, because we're using a mutable reference of a list here. So, those are just like minor implementation details. So we're going to abstract them away, and we're going to add some extra functionality. So the main one is we want to store the current value of the signal so that we can either query it or help us dedupe some of the propagations of those values. So if the value is the same, according to a definition of sameness provided by the user, then we just don't push anything. And in addition to that, we also want to add the ability to unsubscribe from signals. So in this sub function here at the top, we have unsub. And that's just essentially a function that removes that specific signal from the subs container. We're also batching updates. So in this case, you can see that we have provided an API to help us, instead of emitting values immediately, scope them to a particular function call. So if you use batch, it will give you a notify value, and that's just like a token for when things will be called in the future. So what do? We say, signal 1, 2, 3. We keep pushing new values, and we use that notify. And the moment they will be notified is when the scope of that function ends. And this is an important performance optimization, because sometimes we want to, batch a few updates together to prevent re-rendering things multiple times. And on top of this type, we can start implementing other operations like map, filter, reduce, select. Let me tell you a few things about these functions. So with map, we take a function from A to B, and we lift it to be a function from A signal to B signal. The A signal is still there. All of the subscribers of A signal are still going to be getting the values. It's just that the B signal is going to be getting new subscribers with the function mapped so that we can change the value. Filter is interesting because we can't guarantee that the signal is ever going to have a value that satisfies our predicate. So we need to provide it a seed, like a placeholder value in case something doesn't work out. Reduce is like a time machine, because it allows us to look into the future, into the past, I'm sorry. We start with a signal of A's and an initial value, and for the whole history of the signal, we're updating that accumulator. We're essentially collecting, some state over time. And then finally, select is essentially the ability to listen to multiple signals at once, and if one of them produces a value, then the subscriber of the resulting signal is also going to get that value. All right, so there's something fancier that we can do with signals as well, especially using the new, let operators in OCaml, where we can define let and end to sort of help us lift computations to work with signals, as opposed to just single functions. And this some example here demonstrates that pretty well. So we receive two signals, and we, establish this kind of binding between the signal and the values, and we could just write normal code. We can subscribe to multiple signals at once and pretend that we're just working in normal code. But of course, the types are still there to help us differentiate all of the different capabilities that we get with signals as opposed to just normal values. So this means that signals are applicatives. But I know what you're thinking. Signals might be applicatives, but do they have flat roofs? Well, turns out that no, these signals do not have flat roofs. They are not monads. And what this fundamentally means is that we can't flatten them. We cannot have signals of signals. And this is a design choice. It's not something that is forbidden from implementing. You can look into the deep theory behind all of this in resources that I've included there. But essentially, having signals of signals means dealing with some trade-offs that we don't want to deal with. Like, for example, giving up on semantic reasoning, like giving up on the historical reduction of the values, or potentially leading to things like memory leaks and so on. So let's look at another piece of our puzzle, which is just HTML. There's nothing exciting here. It's really boring. None of this is reactive at all. We're just creating DOM elements and putting them in the browser. That's it. Yeah, they do have built-in resource management. So if one of these guys is unmounted, we call a cleanup function. That's it. So how do these two concepts then kind of combine together to get us back to reactivity? Well, we use reactive HTML, and we only need 3 functions to do that. That's all. We might have some different versions of these functions to help us do things more conveniently, but these are like the essential API that we need to work with. So show takes a signal and converts values of that signal into HTML, and it will update that node as the signal is emitting new values. Bind does the same thing for attributes. So if, for example, you want to conditionally say, oh, this piece of text should be red, for example, you attach it to a signal, and then as long as you're producing that red attribute, the text is going to be red. If you decide to change it based on the value of the signal, the text is not going to be red. And finally, each is like a special case of show for rendering lists. The reason it's important is because we want to make sure that we keep around the old elements from the previous render, and we don't unmount them, because show is actually going to unmount the whole HTML node and remount it whenever the signal changes the value. So I wanted to show you some code. So let me do just that. So what we have here is this test that was created by Ty Overby. I hope I'm pronouncing his name correctly. That all right. Okay. Can you see this? I can see it, which is not helpful. That's right. I'll just look at the screen with you. Cool. So this test here essentially tests the ability to compose components using different methods. The most simple one is just rendering a component. The implementation of this component is right here. You can see that it creates a signal, then it has a couple of buttons, like the reset button that sends 0 to the value of the signal, plus will update the current value of the signal by incrementing it using this by argument. So it means that we can externally control the increment value for our counter. So if we go here and start, incrementing that, of course, it just works. So, all right. Now let's look at some more complicated examples. Sorry about that. Okay. So in this one, I added 2 components, and this is exactly the same code, by the way. So the only thing that we're doing is rendering them one next to another. And I mean, this example is also pretty self-explanatory. The state of one component does not interfere with the other state. Then we have this sequential signal example in which the value of the increment of the next counter depends on the initial state of the counter. So if I try to increment, nothing's going to happen. But now, if I increment it by, let's say 5, the increment is actually going to be 5. So let's look at the code for this. All right. We create the counter component. I'm calling it a component, but really it's just a function call. And it returns back not just the HTML. So if we take a look at the type here, this is just HTML. And if we look at the type of count, this is an integer signal. And what happens next is that we pass the count as the increment value to the second component. And by doing so, we're essentially saying, hey, when you increment things, use that signal as opposed to just using 1 or a fixed value. So the next example is about multiplicity, which is having multiple counters. So the initial counter is going to decide how many counters we have. So if I increment this, we get many counters here. And I can increment them separately. I can decrement, and the state persists for the counters that are kept. And finally, I'm going to show you a more complicated example, which is not part of the original benchmark, but I thought it would be fun to have it, which is what I call inception. And in this one, we can still create many, many counters, but if I click on these, they're not going to change, because the increment of each counter depends on the state of the previous one. So if I increment the first one, I can increment the second one, And if I increment the second one, I can increment the third one. And I can keep doing this because the state between them is sort of chained together. And the increment of each one of them decides the state of each one of them decides the increment for the next one. And of course, all of the other properties are still preserved, so we can, remove, add new counters as we please. So this is pretty much it. I just wanted to show you like a small demo of this code. There's nothing magical happening here, and that's like the point. It's kind of boring. It's very explicit. We have the signal type. We can work on that type. We have HTML, which can be rendered. And signals are just values. So we can return them. We can store them. We can put them in the global scope. We can define them locally. There are no like special rules about, oh, you have to like use hook here and like, no, this is just plain boring OCaml with the semantics of plain boring OCaml. So going back to my slides, what I've shown you today is essentially a tiny library that I built called Helix. And it's what I call, the modern approach to building front-end frameworks in OCaml. And I've defined what modern is. It's still experimental. I'm still building it. I'm still iterating on different things. But it has been used commercially in 2 pretty substantial projects. This is just one of them. It's open source, so if you find this interesting, get involved, reach out to me. Really, curious to hear your thoughts on this and your criticism as well. So yeah, thank you.
Thank you. This is a signal for the stop of the talk. And for the QA, do you have any questions?
I'm sorry, I missed the start of the talk, so maybe my question has been answered. But you said it's not monadic, and so you don't have bind. But the last example you show has like signals that depend on the result from other ones. And that feels to me like this would require a bind. And I don't understand how you did the last example, for instance, with the interface you showed.
Mm-hmm. The source code is online. I don't want to show it now because it's a bit complicated, but it does not use bind. The way it works is that it takes the initial counter and it translates the plus and minus into increments to either add an element to a list or remove it. And then what we do is we essentially create signals in a sequence. Sorry, we create components in a sequence where the value returned by the initial counter is used as the by argument of the next one. So there's no monadic state because think about, let me show you one example that might be helpful. No. Exactly, so the actual value is not used. The value is propagated as the signal to the next component, right? So essentially it's a static graph, but what's happening there is that the value rendered is going to be obtained from that signal because you can just query it at any point in time. So whenever someone's clicking, you're like, okay, give me the current value, and you don't need bind for that. We could have bind, and I might reconsider and add bind in the future, but this is very much based on the work done by Elm, where bind has been avoided for a long time, and I think we can just stick to like static graphs of updates, because adding bind essentially adds complexity, and we need to start storing state, or we need to give up on referential transparency because it's complicated. Go and read those articles.
Okay. So I can ask a question. I just wondering, so what you showed basically most vanilla stuff, right? JavaScript, but is it integratable somehow with Melange and other JSOCaml infrastructure? How to use it in real life,
Yeah. It's built with JSOCaml. So this is just OCaml code compiled to bytecode. And then JSOCaml just does its thing and converts it to JavaScript, and you can include it in HTML. So there's no magic in terms of integrating with existing JSOCaml tools. When it comes to Melange, it's definitely doable. I think it's a problem related to tooling as opposed to like implementation details, because we need to find a way for me not to like write 2 versions of this library. And actually, Antonio and I have been kind of talking about this a little bit, where maybe we can use Dune and virtual libraries to sort of have like differences contained in a small library that can be then injected into the main framework. So it's definitely doable, something that I have in my plans for some future work.
Thank you, Rizo, for your talk and for additionally for helping with the organization.